Okay, let's get started. Okay, everyone have fun in the CTF? Okay, so before the class today, we will quickly go over the 4 challenges in midterm CTF. Then we talk about format string vulnerability. So the second half of the semester, we will move a little bit faster. So we will spend just today on format string vulnerability. Next week, maybe also half of the session, the week after, we spend on return-oriented programming. So those attacks are much more difficult to understand than buffer overflow, okay? So stay with me. So there are more advanced attacks, especially return-oriented programming. They are widely used in the wild right now. A lot of attacks, buffer overflow, we learned so far, they are difficult to pull off in real world anymore because of the defense we talked about. So that's why new attacks like return-oriented programming, heap exploitation, which we will also talk about, those are the popular ones in the wild right now. So for the midterm CTF, I already sent you guys statistics. I think in general the class did a good job. I think it's good. So let's quickly go over those challenges. The first one, I actually give you source code. So the source code is here. So the reason I give you source code because this one is a little bit harder than the others. So I give you the source code. You can see in this one, there is a vulnerable function. At the beginning of the vulnerable function, there is a buffer, very small, C code level, just 1 byte. Then I already also print out where the buffer is for you. After that, there is a vulnerable memory copy, which copies whatever you give from the command line to the buffer. So if you look at the disassembly of this one, you realize that you can actually overwrite the buffer, the saved EBP, that's it. You cannot overwrite the return address. So this is a classic stack frame attack, the saved EBP attack. The only difference between this one and the one we studied in class is the buffer in that one is 8 bytes or 4 bytes, maybe 8 bytes. Here is only 1 byte. But as long as you understand how this attack works, so this 1 byte, 8 byte doesn't really matter. What you need to do is to overwrite that saved EBP. That saved EBP points to, if the saved EBP is not overwritten, it's the original one, it should point to the previous function. This is volume, so the previous function is the main function. It should point to the main function's stack frame, right? So it should be an upper location. Your goal here, in that main function's stack frame, it has its own saved EBP and return address. So our goal is to create a fake stack frame, and that fake stack frame will have a return address there. Then we use this val-foo saved EBP to point to there. So when we return val-foo, nothing will happen, but when we return from main, we are going to return to that fake stack frame return address. And that return address, we can just put a shellcode address in. So this is, so that's basically how this attack works. So to pull off that, obviously that address is not the buffer's address. You can, the many ways you can do this. You can put the fake stack frame on environmental variable, or the easier approach is just to put that to the buffer -3. So this is, I think 19 or 20 people got this one. I drop you some hints during the CTF, so that helped some to get this. So that's the first challenge. The second challenge was, most people got this one. So this one was Oh, this is an easy one. So, midterm. So this one is a buffer overflow to overflow the local variable. So the program calls the function print flag. So before print flag, you say there is a compare of EAX with a fixed number. And if equals that number, it will call print flag. Otherwise, it will jump to here, so the program will exit. Doesn't print out anything. If you trace back how we get this EAX, you can say the EAX, there is an integer multiplication. Sorry about that. What's going on? So integer multiplication, so EAX times EAX, basically EAX square. And EAX was from a local variable, and that local variable is from fread. So you only need to overwrite that local variable, then that local variable get the square of that, then so you get the square root of this number, then overwrite that number to that local variable. That's how you can get the flag. That's challenge 2. So challenge 3, 27 people got this one. Challenge 3, did I give you source code? Challenge 3, no source code, huh? So challenge 3, this one is about challenge 3. This one is about the input, right? Yeah. So this one actually look for a specific file and takes that content of file as the input. It doesn't take input from the stdin or command line arguments. So whatever it takes, it will just execute that. So you just need to put the share code in that file. Is it? No. You need to whatever in that file is an exploit to overwrite the buffer. Then you can put your share code in the environment variable. So let's say I have not this one. Yeah, this is basically the source code. So we are going to look for this file, temp input. Then we will just read from that file, read 100 10 bytes, and there is a buffer on the stack, so you can overflow that. Then you just overwrite the return address, put a share code either in this buffer or you put that in the environment variable. The easier way is put that in the environment variable. If you put it in the buffer, you need to calculate how many bytes your share code is. Then you need to calculate how many more bytes you need to overwrite the saved EBP and the return address. So that's the third one. The fourth one, the last one, 7 solved this one, and I do give you source code for this one. So this is the source code. We have the main function print out. There is a function print file. So in this address space, there is no print flag, but there is a function called print file. As long as you specify the name of the file, it will print out the content for you. So it can print out any file's content for you because this is a setuid program. Then there is a valfoo. Valfoo has a buffer, 10 bytes. Then there is a buffer overflow, obviously. So what you need to do is to overwrite the return address of a val so it returns to print file. But when you return to print file, you also need to give the print file an argument, which is the name of the file you want to open. In this case, is /flag, right? But a problem is, where do you get that string /flag? Well, same as you put a share code in the address space, you use the same approach. You put the string /flag in the environment variable. That's an easy way to do that. But if you put a /flag there, you probably cannot have the accurate location, the exact location of that. So you should think about how can I add some kind of padding, some kind of the lob sled for the share code, right? So you can add a lot of just a white space before the /flag, or you can add just more slash. So you can have 500 slash there because 500 slash will be the same as one slash, right? So that can kind of like a lob sled for share code. That you do not need to have the exact location of that string. So this one is very similar to the return to libc attack, which you return to a function already in the address space, but you need to give some string there. Okay, so this is similar to the previous one, like return to libc use system, then call a shell, something very similar to that. So this one I do give you the source code. Okay, so part of the homework this week is to redo all the CTF challenges. If you solved some of them, you can just copy that. If you solved all of them, 3 of you solved all of them, so then you automatically get 45 points for the homework. You don't have to do it. For everyone else, you just need to solve the ones you didn't solve in the CTF, okay? That's part of the homework. That's the homework. So if you go to the website, my website, you will say this week there will be 2 homeworks. The one is to redo the CTF. Another is the homework for this week. So the one to redo CTF, I give you 2 weeks. So from today, you have 2 weeks. This class homework you need to submit next week. Okay, let's go to the second half of this class, this semester. We talk about more advanced attacks. The first one we want to talk about is called format string vulnerability. So this is a vulnerability in C code. This one is a little bit tricky to understand, so stay with me today. So before the format string vulnerability, let's talk about some background knowledge. The first piece of background knowledge is the C function with variable arguments. So you have been programming with C. You have been using functions with variable arguments. For example, you have been using the function printf, but probably you haven't developed a function with different number of arguments yourself. But you have been using that. Printf is one example. So for those kind of functions with variable arguments, when you develop that function, you don't know how many arguments will be there when this function is called. It could be 3, it could be 5, it could be more than that. So to develop a function like that, you need to use the C standard library, std argument. This header file introduced several types. One is called va underscore list, variable arguments list. Then there are several macros there for you to use. They're kind of like functions, like va start, va arg, va end. So printf was implemented using those functions. So in the homework, you are going to implement a simple function, use those things. So here is one example I copied from the internet that how to design a function with variable arguments. So the function we are designing is called average. So given a lot of integers, this function will calculate the average of that. That's it. So the return of integers, the average of integers doesn't have to be integers, right? So the return value is double, but the input, they are all integers. Let's see how to use this function first. Here we use average. So let's say we want to get the average of 2, 3, 4, 5. We just call the function average. The first argument we specify how many integers are there. In this case, 4 integers are there. So the argument is 4 and those 4 integers. The first one is the number of integers. The second line, we call that average function again, but this time we're just getting the average of 3 integers. So we call it as the 3 integers, then those 3 integer concrete values there. So you can see that this is one function. But this function can take, the first time it takes 5 arguments, the second time it takes 4 arguments. But this is one, say, function. So this function is implemented this way. It's just like 10 lines of code. So still easy to understand. The first thing you notice is the prototype. The prototype looks a little bit weird. The prototype doesn't specify all the arguments and their type. Because at compile time, when you code this, development time and compile time, the developer doesn't know how many arguments are there. Okay? So the prototype, the first one is just the number of the input. It doesn't have to be this way. It can be other types as well. Then it's just the 3 dots to say there are more arguments. But at compile time, we don't know. Development time, we don't know what are the arguments. Then at the beginning of the function, we will declare this VA list. This is part of the standard. This is provided the C library. Then we declare sum, which is 0, then index I. Then we use the VA start to, at runtime, we tell the program which argument is our first argument. So we do VA start, we use VA list here, and we tell the first argument is number. That's the first argument. After that, we know how many arguments there. We have a number of arguments. So we just use the VA arg to get each of those arguments. We use, when we get each of the arguments, we tell what type it is. In this case, the type is an integer. Then after that, we go through this loop, so we can get a sum of that. Then, since we already go through all the arguments, we will just end this VA list. Then we just return sum divided by number. So this is how we develop a variable length function in C. And printf, obviously, is one of those functions with variable arguments. So some of you may be coding in C++. So you are familiar with the concept of function overloading. In C++, you can define different functions with the same function name. The only difference is they have different arguments. The return value doesn't really matter. It's the argument. For example, in C++, you can define 2 average functions. One takes 3 integers, another takes 4 integers. And you call the function like this. But this is different from the variable arguments. So for those 2 functions, there are 2 independent separate functions. They just happen to have the same name at the C code level. And after this one is compiled, they do not have the same name anymore. But the variable arguments example, that is just one function, okay? So for example, the previous code, if this is a C version, this is a C++ version. The C version, it's just one function, average. The C++ version, the source code, they actually becomes two different independent functions. And the C++ compiler will change the name of the function as well. So, for example, the first one, we take 3 arguments, right? So the function name becomes average III. So III means it takes 3 integer input. And this one has 4 i's, it takes 4 integer input. And the output is this one probably is not output. I don't remember why they dash z anymore. So the 7 basically tells how long is the original function name. So the original function name is average. So it's 7 characters. That's why it's 7 here. So the same thing here. It's also 7. So after that 7, then it will be the input arguments. So those are 2 different mechanisms. The next we talk about what is format string vulnerabilities. And format string vulnerabilities obviously use something called format string. The format string will convert C data types to a string representation. So to do so, you will need the format string to specify the type of those data. Then those functions can output to stdout, stderr, and also other file descriptors. So the format string controls the behavior of format string functions. So printf is a format string function. There are many other format string functions. Just printf is the one we are familiar with. So the calling function, in this case, is, let's say that we have a format string function, we have a printf, then we have a main function calling printf. The printf will push, the main function will push the argument for that printf onto the stack, right? Then the format string function will use a format string to check each item on the stack. So printf is one example of this. sprintf, also fprintf, also. So you can see all those functions, they are variable argument functions. At the end of that, you always have to specify the first argument. Then after that, it will just be 3 dots because we don't know how many arguments will be there. And you can see printf, the first argument is a format string. fprintf, the second argument is a format string. The first argument is actually where it tries to output to. It's a file string. Then D will just have dprintf is just a file descriptor. Basically, those 2 are the same. Then we have sprintf to print out to a string instead of a file or other places. So all of them, you can see they have a format here. That's a format string, and after that, just the 3 dots. Just to say there are more different arguments. So in this format string function family, there are more functions. There could be like a syslog. There are some arrow functions as well. So not only those functions with printf, there are many other functions as well. So next, let's look at how the format string works. You probably have been using this many times. Whenever you program printf, you are using this. But there are a lot of hidden features in the format string many people are not familiar with. And some of the hidden features can be exploited for arbitrary code execution, override memory. So that's what we are going to look at today. So the format string itself is just an ASCII string. It's a regular C string. It can contain some text to be written. It can also contain some format specifiers that are replaced by values specified in the subsequent arguments and formatted as requested. So a format string specifier follows this format, this prototype. So it started with a percentage sign. That's the one you are familiar with. You have been using percentage %, percentage %P. So it started with a percentage sign. Then after the percentage sign, there are 4 optional fields. So you do not always say them, they're optional. But there is always a specifier. That's why you have a percentage %D, percentage %P, percentage %S. So that S, D, P, those are specifiers. So the percentage sign itself is just ASCII number 25. Between that, there could be some options. There could be flags, with, precision, and also length. Let's see more examples here. First is a specifier. There can be, so how many specifiers are here? There are like 15, 20 specifiers. So you have been using some of them, like percentage D. You are familiar with this one. So D or I just for signed decimal integer. We have been using X a lot. That one is for hexed. And also you can use the uppercase X. So for example, then the output will be uppercase. You can use a float number, scientific notation, character, percentage %C, and a string percentage %S. We also used the percentage %P before, right, to print out the address. So most of them easy to understand, and you have been using it. But there is one specifier most people never used, is the N, percentage %N. Anyone use that before? No, right? So this one is very interesting. So this one is it's not going to print out something to your screen or wherever. It's going to write a number, write some integer in a memory location you specify. And that number is how many characters you have been printing so far in this printf. Okay, we will see more examples of this. So this is the percentage %N is where the problem is. Okay. So the flag side, we have several different flags. So some of the flags, we can use them to help us build a more concise exploit. Also width and precision, but those are not the very important ones. The length is also important. It specifies the length of the data type. It could be, so without specifying this, we just use a 32-bit version, we just use 32-bit, 4 bytes. But if we can use a half, we use H, means 2 bytes, then we do HH, then we can do 1 byte. So later you will see more examples, how do we use this. Okay, next, let's say this example to show you how the format string works. We have 8 different printf here with 8 different format strings. So this box, we have the source code. This box, I have the output here. So the first one is printf character percentage C, note that there is a white space. White space, percentage C, A, lowercase a, and 65. So the printf function will first read this format string, and it says 2 percentages, which means it will look for 2 more arguments in this function, because there are 2 percentage signs. Okay. The first argument, we are going to output it as a character. Since we give it a here, the output will be a, the lowercase a. The second argument, we will also output it as a character. In this case, we gave 65, which is just an integer, but 65 is the ASCII for the uppercase A. That's why we print out uppercase A. The second line, we print decimal, a percentage D, and also percentage LD. L means long in this case. So we just print out 2 values. The third one, we can add the preceding blanks in a number we print. We'll still print out the number 1977, but we are using percentage 10D here. 10 in this case is the length, is the width we want to print out. So for this 1977, we are going to print out 10 characters. But 1977 itself is only 4 characters, right? So that's why we will have another 6 characters as just white space. That's why here there will be 6 white space. Of course, the original in the format string there is a white space there as well. So between this semicolon and 1, there are 7 white spaces. Those numbers are important later when we build our exploits. You will see those numbers are important. We can also specify we do not want the white space as the preceding. Instead we want to use 0, so we can do 0, 10, D. In this case, you can say here we have 6 zeros in front of 1977, and in front of that, here there is a white space. Then obviously we can do decimal, hex, and all others with this. This one is a float. This is another trick with width. Also percentage S will print out a string. So in this case, the first one is a format string. The second one is a string we want to print out. So we just would print out the string. Okay. So any questions with this? Good. So how can this go wrong? I mean, how can this go wrong? This looks perfect so far, right? So the problem is in the percentage n. Let's understand how percentage n works. This is a simple function. There is a foo. We have 2 local variables, a and b. The first one is printf. A is percentage d, b is percentage d, then a and b. So what will be the output of this line? What?
0, 0.
Just 0, 0, right? So this line, we will just say A is 0, B is 0. That's it. Then the second printf is where interesting thing happens. We have changing A and B, percentage n, 1, 2, 3, 4, percentage n, A's address and B's address. So here we're using percentage n. So like I said, this specifier tells printf, you're not going to output anything. Instead, you will put how many characters you have been outputting so far. So how many characters? So before the percentage n, how many characters we print out so far? We print out this bracket. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 15 or something, right? So far, from here to here, before the percentage n, we print out maybe 15 characters. then that percentage n will say 15, and put that value 15 at the address of A. So after this, A will have the value 15. Then after percentage n, we print another 5 characters, 1, 2, 3, 4, 5. So then we have another percentage n. So far, before this, how many characters we print out? 15 plus 5, which is 20. So this percentage n will not print out anything. Instead, it will look for the second argument, which is B's address, then put the value 20 at B's address. So after this line, this printf, the value of A and B will be changed. Okay, do you get it? Okay, most people do not know printf can do this. Okay, but this has been there since the very beginning. Okay, so this is like a hidden feature of format string. Okay, so if after this one, A and B's value has been changed, so we do another printf. A is percentage D, B is percentage D. A will show A is 15, B is 20 in this case. Let's say the second one. I will show you the demo later. Let's say the second example here. We keep changing the value of A and B. So here we have changing A and B. So this part is 15 characters, we already know. Then we have a percentage 0, 20D. So this will look for the first argument, right? This is the first percentage sign, so it will look for the first argument. In this case, the first argument is 50. When you print out 50, it's only 2 characters. But here we're asking for 20 characters, and we're adding zeros at the beginning. So after that, there is a percentage n. But before that, there is another white space. Okay? So before this percentage n, how many characters we print out so far? This part is 15. This part will be 20. So it being 35. Then there is another white space, so it should be 36. Okay? So far, so this percentage n will look for the second argument, A's address, and put 36 into A. Then there is another percentage n will look for the third argument, and this percentage n doesn't print out anything. So still, we print out 36. So A and B after this, both will be 36. Make sense? The third one, actually the same, just we're using float numbers. Here, the precision is 2, the weight is 10, so we are output what, how many? 12, 13 characters there. So if we run this program on the server, you will see this. Let's see. Okay, I miscalculated there. It's actually 41, so not 36. So at the beginning, A and B are 0. After we change that, A is 20, B is 25. Okay, so this part is 20. This part is 20, not 15. Then the second one, this part is 20. Then we have this part also 20 because we have a 0, 20D there. Then I will have a white space. That's why this one is 41. B is also 41. This part is 20. Then we print out floats. This one is 38. Okay, so you can see that the key here is the printf, the format string functions. They can change the value, the location you specify. So you can say this can be. So what if when you program this, you do not specify A's address or B's address? It can be any address. So you can overwrite any address in the memory space. So there actually have some other extensions for format string. The proxy extension, they support the $sign as well. We're not really using this, so I put a slide here, so if you are interested, you can read this, but we're not really using this. So we're more interested in how we can really exploit this. So now we already know what format string is. We know the %n is dangerous. We can overwrite things. But how do we actually exploit this? And how do we really have a vulnerability here? So the vulnerability exists when the user can specify the format string. So previously, all the printf, the user cannot specify the format string. All those examples here, which one is a format string? The first string, right? That's a format string. The first string with %sign, that's a format string. But those format strings, they are hard-coded. As a user, you cannot specify that. So when you cannot specify this, it's not really a vulnerability. But if the user can specify that, it becomes a vulnerability that we can exploit. So here are two examples. If this is a user input string, if you just do printf user, so what will happen? That user input string will be treated as a format string. And this is wrong. But a lot of code we had before, they just use printf like this. So this is a vulnerability. So if we do this, it will not be a vulnerability. So let's say our first example here. How do we exploit it? We have a val foo. The val foo has a buffer, 20 bytes. Then we call printf twice. The first time we call printf, what is your input? That's it. So this string is hard-coded. This is a format string without a format specifier, right? We're not using percentage anything in this format string, but it's still a format string. That's the first one. So it will just print out this. So this one, there's no vulnerability. The second one, we have gets. So after gets, we're going to type something, and whatever we type, we're put inside that local variable s. We put it there. Then we have another printf. This printf is what the vulnerability is. This printf will directly use that s as a format string, and that s is what we specified. So it can be %x, could be %n. That's it. We don't return it. So then I needed you to think here what will happen when we run this program. Okay, so let's say my input is %x. What will happen? This is a source code. My input is %x. What will happen here? That %x is a format string, right? It's a format specifier. This one will be used in the second printf. So basically, the second printf will be printf %x. What is %x? Specify looking for a number on the stack and print out in hex, right? But we didn't give that. we didn't really give the argument here. That's a problem. We didn't really give the argument. So whatever the inside printf, there will be a pointer point to somewhere on the stack. Then we will use that number to print out. So when we do %x, it will just print out some value on the stack. We don't really know the exact location of that value, but we know that value is something on the stack. In this case, it prints out this number. That's a number on the stack. So if we do, instead we do %d, it will print out the same number. So this one, F7, and this one is the same number. That's a number on the stack. So by doing this, we have an arbitrary, well, not really arbitrary, but we have an information leakage vulnerability here. We can pick what is on the stack. We can do a lot of %x here. So to separate different values, I use a dot. You don't have to use dot. You can use other symbols as well, because those symbols will be just print out as a character, right? So you can use anything as a like this. So I'm going to print out 5 different things on the stack. So those are the values on the stack. Some of them 0. Hey, look at this one. What is this one? 5655. Looks like a function address, right? Or code address. So that is probably the return address on the stack. That looks like a return address or function, or let's save the EBP. Okay. Then what will happen if I use %s? So %s will print out a string, right? So what is the argument it looks for? %x will print out a number, and the argument it looks for is an integer. %s will print out the string. The argument for that is what? Is the address of that string, right? So it will treat some random data on the stack as the address, and dereference that address, try to print out the string. Make sense? So if that address is not a valid address, what will happen? It will be a segment fault, right? If dereference an invalid address, we will get a segment fault. So if I do this, very likely we are getting a segment fault. But in this case, we already know what x is. We know x is this value. So when we do this, we'll dereference this address. So that address doesn't look like an invalid address. So probably we do not say. So we do not get a segment fault in this case. However, if we have 2 %s, what will happen here? We already picked the stack. We already know what is on the stack. On the stack, the first item there is F7. The second is 0. So when we do the first %s, we are dereferencing that address, which gave us the string u dot. Okay, I don't know what is that. I don't know why it's there. But what about the second %s? We are going to dereference the second one, right? Which is 0. So what will happen? That's a null pointer. What will happen? But different there, we get a segment fault, right? So if we do this, this one doesn't really give us a segment fault. It prints out null. Okay, good. So if we do more s, some of them could be invalid. So eventually give us a segment fault. Okay, does that make sense so far? Does that make sense? Okay, let's look at the disassembly this one and try to make some sense out of this crazy stuff. So the left-hand side, I have the disassembly code of that. Did I call it Valfu? Oh yeah, the Valfu. The right-hand side, we have the stack. So at the beginning of this function, same as all the functions we have been looking at so far, at the beginning, we will have the return address on the stack. ESP will point to the return address. Then after several instructions, the stack will look like this. There is a canary here, stack cookie there. Save the EBPs here. Canary is at EBP minus C. Then we have the gets. The gets will output things in a local variable S. And local variable S is at EBP minus 20 here. Okay, 20 in hex. So this part is 32 bytes. Then, after gets, we will call into another function, which is printf. So, which means the stack will keep going down, right? Because the printf will also use the stack. So, when we are in the function printf, our ESP points to somewhere down there. The value we do not really know what it is. So, but by specifying percentage x there, we will be able to print out everything from here to up there, right? As long as we give enough percentage x there. So which means if we, let's say the x here we put is percentage x. So if we put enough percentage x here, eventually we are going to print out the string percentage x dot percentage x. Does that make sense? Because we're going to print from here to here, right? So what is percentage in ASCII? 20 or something? So if we run this program, we give it another percentage x here. Oops. Oh, this one is too much. Because we can only write, hold on. This whole thing will be copied to S. S is only 20 bytes. So here, how many bytes we're saying? This is 3, so that's 12. So this should be okay. So by doing this, we are printing out things on the stack. But that's not enough to reach. That's not enough to reach our the string itself. So we can print out the stack, and we can also crash the program. So does this make sense to everyone? Why we can pick the stack and why we can crash the program? Does it make sense? Okay. Then let's move to our second example. In our second example, we are not trying only to pick the stack. We are trying to pick some secret in the memory. So there are two global variables, two pointers, P1 and P2. They point to two strings. So those two strings are not in the stack, right? Instead, they are in the .data section. But we have those addresses. In the main function, we print out the secrets at those two addresses. So can you read them? So if we run this program, format string 2, we run this program, it will print out the secret at that address and those address. Then it will ask for your input. So you just input a random number, obviously, it will not give you anything. Let's say, how do we exploit this? Then we have this val foo. Val foo has a temp buffer, 120 bytes. Then we have gets, where put what are your input into that temp buffer. This one, there is a stack cookie, so you cannot do a direct buffer overflow. After that, there is printf temp buffer, which means whatever your input will be treated as a format string, right? Then it's just the return 0. So how can we exploit this to print out the two secrets there? We know there are two secrets. So the idea is this printf. We want this printf to print out something. The parameter of that printf should look like something like this. It will be, first of all, a printf. Then first there is a format string. And that format string, how do we print out a string? %s, right? So it should have two %s. So we can print out the two strings. But to print out the first string, the second argument should be what? The address of that string, right? So this should be the P1. This one will be P2. That's what we want. And this one, the program print out for you. So first of all, you need to put those two values into the address space of this program, right? Or on it would be best if we put that onto the stack. So what we do is so there is a stack cookies here. We cannot directly override the return address. Oh, anyway, that's not what we are trying to do anyway, right? We are trying to get those two secrets. So our input will go to the temp buffer, and this temp buffer is at this address. Can we put those two addresses at the beginning of the temp buffer? We can, right? We can put, it will print out those two addresses. We put those two addresses at the beginning of the temp buffer. Then we use %x. We are going to look for the next argument. Make sense? Eventually, it will find the argument. It will treat this address, whatever here, as our argument. Then instead of using %x, we use %s this time. So %s will use this one as the argument, and this one as the argument. So it will print out two strings for us. So let's try this. So we have two addresses here. So the exploit will look like this, Python 2. So we first put those two addresses there. So first 08, 70, 55, 56, then 1A, 70, what's going on? 70, that's weird. 1A, 70, 55, 56. Okay, so if we do this, what will happen? Look at the source code. When we do this, we are going to input 8 bytes there, not necessarily printable, but those 8 bytes will be sent to printf, will be print out. But some of the characters are not printable, so we're not going to see all of those 8 characters. Some of them may be printable. So when we do this, this is what we get. So basically, those are printable ones. So this one is not printable. Those are printable. This one is not printable. That's why we got a PUV there. Okay? If we say ASCII, is this big enough? Let's see. Can this make larger? Okay. So we have P, lowercase p, uppercase U, and uppercase V, right? So lowercase p is just 70. We have 70 there. Uppercase U is 55. Uppercase V is 56. So that is what our input. So that's why it directly print out. Then we want to print out, we want to find this string on the stack. So how do we do that? We just do I use several underscores to separate things, so we know they are not the same thing. So we do a percentage %x. We're going to so this one we need to put into a, let's say, so what is this program? This program takes from std in format string. Okay. So this is my exploit. I have two address there, then two underscore, then percentage %x. The whole thing is sent to the vulnerable program as a format string. And a vulnerable program will first print out the secrets are at those two locations. That's the first printf, low vulnerability. The second printf will treat this one as a format string and print it out, right? So the first, those 8 bytes, 3 bytes are printable. That's why 6 bytes are printable. That's why we get PUV here, PUV twice. 2 characters are not printable. We do not get anything. Then we get this underscore. Then we get this percentage %x. It will look for something on the stack. It will print out something on the stack, which is FFD6-2B. So that's not something we can recognize. So we keep print outing things. Let's say, let's do, why do I forget this percentage? So let's do 3 of those, maybe 4 of those. Syntax error somewhere. Oh, what I'm doing. What I'm doing here. This one is a format string. So the format string is here, okay? So I do another percentage %x, another percentage %x. So we are going to read 4 items on the stack. So let's see what we get. We get FFD6C2556. So that looks like an address. Then another 55. So still, we do not have what we're looking for. We're looking for that PUV. Why my computer freeze here? What's going on? Percentage %x, percentage %x. Okay, do we find that PUV? This one looks like that, right? Yeah, but hold on. I have another typo there. There should be a percentage %x, not x. Oh, yeah, we actually got it. You see? Those two. 5655 7808, 5556 7818. That's our input. That is our input. See? So our input we put our input, the format string, in that temp buffer. And in printf, we start looking things from lower address by doing many %x. Every time you look for next argument. Eventually, it will reach at the location where we put our input. So from here, how do I change this exploit? I only need to change this a little bit. Then we can print out the string, the secret. How do we do that? What? Change which one to %x? Last two, right? Okay. Okay, you do understand what's going on here. Good. So we change. So we change the last two to %s. Then it will use those two as the address and dereference that address to get the secret. Okay, so now we print out the secret. This is a secret one. This is secret two. Okay, those are the two secrets. Okay, but before that, we still print out those things on the stack. Then we print out the secret. Okay. So that is our format string. That's our format string number 2. So this is what the exploit looks like. You don't have to put that into a file and do that. This is just go to std. Okay, so let's take a break from here. Then after we come back, let's see how we can actually get the flag or run arbitrary code by exploiting this vulnerability. 10 minutes break from here. That one covers many different topics of computer security. Yeah. So it's more like an introduction course to system security, network security, applied crypto. Okay. There will be a little bit software security module. Okay. We will cover buffer overflow a little bit, but not like this. Yeah.
But it's not hands-on.
Well, not as hands-on as this one. There will be some coding assignments. I don't remember how many. I know most of 3. Yeah. Yeah. Different from this one. Yeah. inside the implementation of printf. So we only know it will start with somewhere, in the printf's, or you can say, so this is printf stack frame, right? This is printf stack frame. So printf it will have its own return address. It will have its own saved EET, right? Then it will have several arguments, right? So the arguments will be the address of the format string. The address of the format string, right? And then the second, so everything after that will be the second argument, third argument. So you make it, you do a percentage x. Let's say you have a format string, then you do a percentage x. You make the printf believe it has a second argument. Then you will look for it. Make sense? Then if you have two, it will look for even move up. Right? So it's on the stack frame of the printf.
So the deployed script, let's see, here's the first one, percentage x, and here.
Yeah.
Here's the second one.
Yeah.
So is that like some
Exactly. So yes. So this is the main function. This is the ball tool. Holds this. Right. So the value will be just some value on ball tool. The stack. Yeah. It could be eventually reach to our buffer, which we have a string format string. Make sense?
So it's basically like first x from there and then several x going up.
Yes.
Until we reach to the holes.
It's actually already this the whole thing is the buffer's stack frame, but the buffer's return will be here. So if you keep reading, you will read the buffer's return as also. You will be able to read.
So we are like basically from the first argument and then all the way up.
Because the first argument will be the string's address. Right? Yeah. So printf where because you specify percentage x, printf will believe there is a second argument, but there is none. That's why you will trick something there. Yeah.
So basically like read from first design actually from here.
Yeah.
And the second one.
No, the first one it should be here. First one should be here. Oh, this is the first argument.
And then the second one and all the way up to
Yeah.
return.
Yes.
Thanks.
Yeah. Sure, of course.
Professor, we have this on the server.
What?
PNGB Vulkan. I kind of went through this and.
Do we have what? No.
This, no, you don't have
No,
that.
we don't have that. Yeah. Well, I asked the TA to install that, but he was not able to.
It does explain a lot. I mean, it's a little clear.
Yes. Sure. The TA was not able to. Well, that's why I need a lot of help on our platform. You can say our platform. We need to install a lot of things there. We haven't. Yeah. Yeah. If you're interested in the content, you can help. Yeah. Okay, looks like some of you are not sure what happens here. So I should have drawn this one on my slides, but I haven't. So I will add this to my slides later. So we're looking at this function, okay? This program. So we have val-foo calls printf. Val-foo first calls gets, right? But after gets, we call printf. So when we call printf, this is what the stack looks like. So this is the stack high, it's high, this is low. So we have val-foo, we have the return address, which obviously is the address in the main function. Then we have saved EBP. The saved EBP obviously points to the main function's saved EBP. Then after that, the val-foo has its own stack cookie. After that, it has its own temp, local variable, the temp buff, which is 120 bytes in this case. So there could be some paddings between. We can only figure out how many bytes are there by looking at this assembly. Then after that, there could be other some padding there. Then eventually, so we don't have gets anymore. Okay, gets is already done. So now we will have the stack frame of printf. So what will the stack frame of a printf look like? It will also have a return address. This return address obviously points to somewhere in val-foo. Then you have saved EBP. Saved EBP points to the saved EBP here, which is val-foo's stack frame. Then higher than that, we will have the parameters, because the parameters goes to stack in 32-bit. So in this case, we only have one parameter, which is temp buff, which is the address of the buffer. So here we only have 4 bytes. That 4 bytes points to the real buffer, which is at a higher location. That's it. But when this printf, when we give it percentage x, or we give it, let's say we give it 2% x, then it will believe there are 4 arguments for the printf function, including the format string itself. The format string is the argument, right? Then there are for each percentage x, it will look for the next argument. So where does it look for the next argument? Obviously, this is the first one. So the next argument will be 4 bytes up, will be here. 4 bytes higher, that's the first argument. So this percentage x maps to here. The second percentage x maps to here, another 4 bytes. 4, 4, 4, right? So if we give it enough percentage x, eventually we're going to read into the temp buff. We can also read to the saved EBP or return. We can read anything beyond this. Make sense? Okay. So that's our format string number 2. Okay, let's go to format string number 3. And this is the one we're trying to get the flag. We have val-foo here, which has the first buffer, the second buffer, 2 buffers. Then we will have a fget. The fget will read 99 bytes, including the new line, so 100, to buff2. So this fget, we cannot overflow the return address, right? We cannot. Because this is exactly the size, actually 1 byte more than the buff2, so we cannot overwrite that. However, we're going to do a printf buffer 1, buffer 2. So in this case, buffer 1 is a target, buffer 2 is a format string. So your input will be the format string. So your input is at most 100 bytes. But that 100 bytes is a format string, so it can generate more than 100 bytes. Make sense? For example, like a percentage 20D, that is only percentage 20D, that's only 4 bytes. But the output of that 4 byte, of the format string, is 20 bytes, right? So your input is 100 bytes. But the format string that will generate more than 100 bytes, so you will be able to overwrite the buffer and beyond, because you are writing it to buffer 1. So this one, so use format string. The first is a format string, then there is a buffer overflow to overflow the return address. So if we look at the what I'm trying to do. Let's do a check sec here first. Check sec. So this one, there's no stack canary, so there's no cookie, so we will be able to override the return address. Then so how do we get a flag? So the stack is executable in this case. So what do? We first put the shellcode in the environment variable. Well, we can put the shellcode in the buffer. This is big enough, but shellcode will be easier. We put the shellcode in the environment variable. We get the shellcode's address. Then we overwrite that return address. Yeah, that's it. It's actually easy here. So let's put our shellcode there first. Where's our? I should have shellcode. Create a new one. 600 bytes. This part looks. So here we should remove this one. Okay, let's see. We first put our shellcode there. It's good. Looks correct. So we have our shellcode there. We have our shellcode there. Then we look at where is that buffer. This is our waffle. We have fgets. Fgets is to put your input into buffer 2. So buffer 2 is at EBP minus D0. Then the sprintf, here the sprintf, the first argument of sprintf is where the buffer 1 is. So buffer 1 is at EBP minus 6C. Okay? So how many is 6C? Next to decimal. 6C is 108 bytes. Okay? So that's why the stack actually looks like this. Buffer 2 is at a location doesn't really matter. What matters is buffer 1. Buffer 1 is at EBP minus 108, which means we are going to generate some garbage, which is 108 bytes. Well, 112 bytes, because this one. Then we have the return address. Okay? So this should be easy. we have that. So where's our shellcode? Our shellcode is there. So our exploit should look like, so this one is fget from std_in. So whatever we put there is a format string. So let's do percentage %d, how many? 112, right? That makes sense? So this one, percentage %d 112, will print out an integer, and the total length will be 112 bytes, right? So that will override buffer 2 plus save the EBP. So this one will look for some value on the stack, but we don't know what that value is, and we don't care what that value is, right? And then after that, we will just have the return address. So which should be, let's do 60 DC FF. Okay? Then this one pipe into format string. Okay? That's it. Very easy, right? So if we do not do 112D, let's do 110, 108. We're not going to overwrite the return address. We're only overwrite the saved EBP, so this will not work, right? We get a segment fault. So if we do 111D, the same thing. We will be 1 byte off, we'll get segment fault. That's why we do 112D. So like I said, the 112D, we can also add some padding here. So right now, the 112D, the padding is white space. It doesn't really matter what the padding is. We can use 0 as a padding. So it will give us the same thing, right? Okay, this one makes sense, right? This one is easy. Let's go to the next one. Of course, you can also put the share code inside the buffer. That's what I used to, but here's the thing. If you put the share code inside the buffer, no, this one I put the share code after the buffer, so this one is good. If you put the share code inside the buffer, then you need to calculate how many bytes your share code has. So change that to 112D accordingly. So I put the share code upper there, so that's fine. Let's say one more example. No, 2 more, I believe. Yeah, but this is where things get interesting. Let's say the first one. Okay. So this one, so far we're not using %n, right? No, so the previous example we're not using %n. The next one we're going to use %n, I believe. Okay. So this one we have a global variable auth, which is initialized to 0. And in the main function, if auth is not 0, we're going to print out the flag. That's it. The valfoo has a format string vulnerability, but no buffer overflow here. We have a buffer, 512 bytes. The fgets will get 510 bytes plus /a/0, /a/then, so it's 512. So there's no buffer overflow. The fgets will not cause any buffer overflow. However, this string will be input as a printf, so there will be a format string. So the goal here, so any idea how to solve this one? Obviously, we want to change the value of auth, right? Obviously, we want to change that. Then, to change the value of auth, we can use %n and the address of auth. As long as we know where auth is, then we use %n, we can change the value of it. So, similar to this one, we want to put the address of os at the beginning of the buffer, which is here. Then we use %x to pick the stack to find out how many %x we have. We need until the %x maps to the address of that os global variable. Then we change that %x to %n. Then we can overwrite that, right? Let's see. So this one will look like format string 5. So the first is to find the address of os. So we can use nm to do that. We do nm. This nm will show us all the variables and their address. Then we just do a grep os. You can say os is at this location. We know the address of os. Of course, you can also debug the program. You can also find the address. Then the format, the export should look like Python 2. Let's put the address of os at the beginning. So it will be 34, C0, 0408. Then after that, we just have some %x here. We pipe that into format string. Okay. So the program does print out the return address for you, but I don't think we need to print the return address of this. Do we? No. So this one is to override os. So we don't need the return address here. So let's say the first 4 bytes are not printable. That's why we didn't print out anything. Then we print out the 2 underscore. Then we pick the stack. We get 4 values. We do not look. Do we have that? No, we don't, right? We have 0804 41B4. So still not there. Then we keep changing. We'll keep adding %x. Oh, 0. Still not enough. Oh, do you see it? We find it after this one. This one. So if this is a little bit confusing, we can make everything aligned with we add a width, which is 8 here. So every value we will print out 8 characters. The padding will be, let's use padding 0. So this will make it look a little bit better. Okay, look a little bit better. So you can see this one. We do have the address we input there. So the last 2, we don't need those 2. We only need this one. We change that to n. That's it. So the last %x, we don't need them. Then this one we change to %n. Okay. So how many? So then os will be changed, right? Because now the %n corresponds to this one, which is the os's address. And so far, how many characters have been printed out? So there are at least 2 characters. There are many characters. So several, 30 or something. So os will be changed to 30 or 40 something. So os will not be 0 anymore. So this should work. Let's see. Yeah, it works. See? It print out the flag, right? Because we changed the os. So if we have another percentage x here, it's not going to work, right? We have another percentage x, what will happen? This percentage n will correspond to this address. And this probably looks like it will trigger a segment fault. So we are going to write to that address, which we probably do not have permission to write. So it will get a segment fault because of that. Okay? So this one is to change the os, and we only need to change os to non-zero. The next one will be a little bit trickier. We have to change os to a specific number. There are two different os and os1. The first one is 60, the second one is 80. We have to change to that specific number. Otherwise, it will not print out the flag. To help you debug, I do print out the os number here. What is the value of os to help you debug this? Okay, any idea how do we do this one?
So we control the padding of 3 digits.
Yes. Yes, but here we need to change two variables, right? So we change the first one to 60, then we add a 20, kind of like 20 bytes more, then we change the second one. Okay, so format string 6. So we first get the address of those two. Oh, what I'm doing? Why? I should do a grep. Grep auth. Okay, we get the address of those two. They're actually adjacent. Then we are going to say we first put those address there. You don't have to put those two addresses at the beginning, right? You understand that. It's just easier if you put it at the beginning. 34, say 0, 04, 08. C0, 04, 08. Okay, so after this, we so why just print out 8? Why it's printing out 8 there? Print F. Oh, we print out this here, do we? Oh yeah, we do print out those. The 8 here is what? Oh, this one, 38. That's why we have an 8 print out here, because we have a 38 there. Okay. So we start look for those address. So let's add a dot here, percentage %x. %x. Oh, so, okay, we find one of those. We need one more. %x. Okay, we find those two addresses here, which is this one and this one, right? So if we change those two values, we can override os and os1. But let's say if we change now, what will be os? Os will be, so this one is like 8 bytes, 8. That will be 16. There's a dot, another dot. That will be 18. Then another 4 or 5 here, 5 here. So it will be 23 bytes, right? So OS1 in this case, or OS in this case, if we change to percentage n, will be 23, something like 23. So this one will also change to, let's say, we change this one to n, this one to n. So OS will be something like 23. OS1 probably will be 24 because there's a lot of dot here, right? So it will not give us the flag, but let's see if the value is correct. Oh, my calculation was wrong. So we have 31. So those unprintable ones will also count? I don't remember. Maybe those unprintable ones will also count. Let's count here. So if we count those all unprintable ones, so here we have 8, 9, then we have that one will be 9, so this one will be 4, 9, 9. How many is that? Let's change this one. Change to 8, 0, 8. So this will be clear. So at the beginning, here we have, this is 9. This is another 9, 9, 9. So that will be 40. Oh, yeah, exactly. So even those unprintable ones, they will also count. So this one is 9. This 8 plus a dot, that's 9. This one is 8 plus a dot, 9. So we have 4 of those. So we have, that's why we have 39. Because we have 3 percentage x and the beginning of that, right? So it's 36 bytes. Then after that 36 bytes, we have a lot of dot here in this one. That's why we have 37, right? So how do we make this? The first one we want to make it to which value? 60, right? 60. 60 is easy to, this one is easy to achieve. So we just add, we need another 14. No, we need another 24, right? So we just add this another 24 here, so 32. We change this to 32. So, okay, so we get the first one, we get the OS to 60. So after OS, so after this one, we already printed 60, then we need another 20 here. We need another 20 here, which means we can add, maybe we can add the 20 dots here, right? That's one way to do that. What if we do not want to add 20 dots there? We want to add, well, the most easier way seems like still 20 dots. That's 3, 4. Okay, that should work. Okay, so when we do that, we add 20 dots there. Obviously, it's, what if the number is too big? Then we cannot add 20 dots there, then we can add a percentage d there, right? But this is the tricky part. Let's say in the middle of this, we add a percentage d 20. Will this work? This will not work because that percentage d will map to our address here. And that percentage n will map to this part, which is not a valid address anymore, right? So which means if we want to use a percentage d in the middle, then we need to add something here to match that. So the value here doesn't matter, then we put this. Then this changes a lot. This changes everything in front, actually, right? Let's see. We're actually close. So this one, we do not need 38 anymore. We need 28. 32, we change to 28. Then this one is 20. Oh, it should work, right? It should work. Okay. So this one also works. So you can say that this one we can change different, we can write arbitrary address in the memory space, which means we can also overwrite the return address. Here we are overwriting those two global variables, but we can also overwrite return address. that brings us to the next challenge. It's actually challenge 5. But this one, we're not going to overwrite the global variable auth. We're going to get the flag here. How do we do this? We're going to overwrite a code pointer. How do we do this? Any idea?
Override the return address on the overflow.
Okay. So then we will need to know where is that. We use %n, but we need to know where that is, right? So this is the idea. We are going to overwrite the return address of valfoo and change on the valfoo stack frame, and we change that to print flag. But here is another issue: is the value, the content we overwrite is the number we print out, the number of characters we print out so far. But this return address is a huge number. Can we print out that many characters? It would be hard to print out those many characters, right? It may take forever because it's 4 bytes. So the trick we use here is we do not overwrite 4 bytes once. We write 1 byte a time. Okay. We write 1 byte a time, but a %n cannot do that. That's why where we have that precision. We have that precision. Not precision. That length. So we can use that length. To override 1 byte, we do not use %n, we use %hn. Then we just overwrite 1 byte there. Okay. So, yeah, the exploit will look something like this. I think this one I actually play a little bit tricks there. I didn't overwrite all 4 bytes because the first 2 bytes, they stay the same, right? Because I'm going to return to print flag. And the print flag has the same first 2 bytes as the main function. So I do not overwrite the first 2 bytes. I only overwrite the least significant 2 bytes. So I just need to do that twice. And here we need to do some calculation, how many bytes we need. And also there's another trick is, if you override the first byte, the number is very big, let's say FE. The second byte you want to overwrite is a small number, like 3E. So how do you do that? Because you keep outputting. So the number of characters you output so far will keep going up, right? But how can you get a smaller number? You overflow it, because we're doing 1 byte. You overflow that, so 257 is the same as 1, right? So you overflow it. So this is what the exploit looks like. Okay, so that's all for today. So we still have 1 hour, so you can start working on the homework. The homework is the format string. So I will work around there to help you, because this one, I think this one is a little bit tricky to understand. So if you have questions, just ask me. So next week, we are going to talk about something even more powerful and interesting. It's return-oriented programming. will be homework line, the format string ones.
but you cannot write to this address. You can only write to the address when the percent x is unique to that point. Yes.
Now, right?
Yes. Let's say at the beginning you don't have percentage x, percentage x. That's what. Instead you were use a percentage n at the beginning. Then the second argument, percentage n, you also look for the second argument. The second argument
So you can see what I did here is I add 20 20D there, right?
Yeah.
So that 20D will correspond to this one, 11, 11, 11, 11, right?
Oh, you
Yeah,
added
so so obviously the value 11 doesn't matter, right?
Yeah.
It was just that, right?
Okay, I didn't see this part.
Make sense?
Yeah.
Sure. Well, so this one got 60 is n because before this, the whole thing here is 60 characters. Now after this is another one, that's why before this is 60. So the inner one is just n. So it means in between those two, you need to print out 20 characters. So you just need to do whatever. Right? That's why we can do it. Right? Like this. Yeah. If you want to use format, the way I want to do it is like, so between those two will be 20, right? So we just percentage G. But the problem here is, so between those two, there will be 20. However, this one is a specifier corresponds to this one. You see? So then this percentage n corresponds to some garbage here. So this will trigger signal here, right? This will trigger signal. So what it do is, that's why you need to 4 bytes here. Let me just for garbage